This 3.3 section, that is isotopes and radioactivity. In fact, if you are asking me, if you are asking any chemist actually, the radioactivity or its history, I have to say it is one of the remarkable breakthrough in the science, which paved the way for development of development of energy sector and radiation treatment and food treatment for killing the germs, and there are a lot of developments happened. Actually, it is one of the see, nobody will believe, right? Okay, suppose if if an atom, it contains some energy in the form of radiation and all. So is the remarkable development of radioactivity and isotopes. And we are well known about the scientist Mary Curie and her husband Pierre Curie. So lot of development, lot of remarkable and lot of unparalleled developments happened in the case of isotopes and radioactivity. Okay, so now we shall see what is radioactivity. Sorry, isotopes. See, for example, the carbon atom. All carbon atoms, it is having the number of protons, 6 number of protons. Okay. So, but do you think all these carbon atoms are similar? And actually, no. In fact, see, this is a carbon atom. So this is C12. So this got a 6 electron, 6 protons, and 6 neutrons. On the other hand, there is another carbon atom which has nucleon number 13. Here the nucleon number 12. Here the nucleon number 13. See, here it is having 6 electron, 6 proton, but 7 neutron. Okay, and C14 on the other hand, so here it is, here you can see, right? Okay, I'll draw it. C14. So it is 6 electron, again 6 proton and 8 neutron. Okay, so this is the case. In fact, here this is this C12 and C13, that is normal elements. It doesn't dissociate, it always remains. These are very stable nucleus, it doesn't dissociate also. Okay, and here C14, it is also called a carbon 14. It got a nucleon number 14, this got a nucleon number 12, this got a nucleon number 13. Okay, and here this C14, actually it is it is one of the radioactive element. Okay, and it got it all got number of protons and number of electrons same, but it got number of neutrons. Number of neutrons are different, right? And in this C14, it is a radioactive element. The radioactive element in the sense, see, this doesn't remain like a C14 for a long time. After some time, this C14, okay, it decomposes into N14 plus beta particles. Okay, N14. So here it is 6. Of course, here it is 7. So due to the loss of electrons, okay, due to the loss of electrons, it this is the decomposition reaction. So if this decomposition, it results in the energy, and this results in the release of energy, we can call it as a radiation. So this radiation, due to the release of this energy, this C14, it is one of the radioactive nucleus. That means it releases a lot of energy. If we are keeping for long duration, okay, it keeps on releasing the energy. Okay. Now, one thing you need to know, these other elements, other forms, so C12 and C13, okay, these are not radioactive. It doesn't release any energy, it doesn't decay also. Okay, and this decay, it is a for the C14, it doesn't decay for like immediately. In order to suppose 100 atoms of C14, in order for it to become 50 atoms. Okay, so that means 100 atoms of C14, it decomposes into N14. So in order to become 50 atoms, it requires almost 5,733 years. Okay, 5,730 years it takes. Okay, and now you need to know one thing. This this is the case of C14, but not with all elements actually. For radon, okay, radon 220. So this is just a few seconds, so say like a 55.5 seconds. That means, if I take 100 atoms of radon, almost for 2 minutes, within 2 minutes, this radon got decomposes into another nuclide. But on the other hand, for cobalt, so cobalt is 60. So this got radioactive, half-life 5.26. By the way, I missed on time. See, in order for this 100 atoms to change into 50 atoms, so that means how much, right? 50%. This is 100%, 100% to 50%. Okay, it will take 5,730 years. This time period in which, from 100 to 50, we call it as half-life. Okay, half-life. Okay, so half-life for radon it is 55.5 seconds. For half-life for cobalt it is 5.26 years. Okay, and for half-life for potassium, okay, it is 1,300 million years. Okay, so this is something you need to know. This decay, it is a very it is a random process. It keeps on happening without any delay. The decay, suppose so this is 1,300 million years. Okay, there is a decomposition of K40, potassium 40. Continuously it is going on happening. Okay, and here okay, see this due to the nature of this radioactivity. See here also this carbon 14 it is emitting radiation. Same way, cobalt also it emits radiation. Radon also it emits radiation. For example, this something which is having very less number of half-life. For example, radon 100. Okay, it releases the energy instantly within very short span of time. It releases lot of amount of energy. Okay, more amount of energy. I cannot say lot of amount. More amount of energy it releases. Okay, and what I can say is due to the release of this energy, working with the radioisotopes, it is very challenging and it is dangerous. So you can see the glove box. Here, someone who will be putting their hand inside through the glove box and then they will be working. Okay, and it is not like something you take using barely in your hand, something what we do in our common wet laboratories, or say using the glass apparatus we will be pouring the chemicals. That way you cannot work with the radioisotopes. In fact, in many countries, of course not in many countries, all the countries, in order to work with the radioisotopes, you need a specific license and specific laboratory apparatus and specific requirement. Unless that, you cannot get a permission, and if you do that, you will end up in jail, because the radioactivity, once it falls on your body, it can lead to severe health consequences. Initially, you will feel vomiting and headache and nausea sensations, and for after almost for 1 week, if you get a severe radiations, maybe maximum 2 weeks, that person may end up in death. Okay, yeah. See, take a knife. Consider this is a knife. You can use it for killing somebody, as well as you can use it for cutting the vegetables, right? So the same way, even with the radioactive isotopes, there are disastrous uses. We all know, most of us heard about atom bomb, what has fallen on Nagasaki and Hiroshima. So it has killed a lot of people. Yeah, of course we know about a nuclear bomb. But how many of you know the positive side of this radioisotopes? Of course, the tendency for human beings is they often look into negative side, but they often overlook what is the positive side. See, the radioactive isotopes, it got a lot of positive uses. For instance, to check for the leaks. Okay, so see, consider this is a oil pipe. So here there is a leak. So yeah, the oil will be running. And if you want to know about the leak, if there is a leak in this one, yeah, so this oil, it will be falling, right? It will be going out. So this is a oil pipe. So in order to check for the leak, you can just input radioisotopes. Okay. So this radioisotopes, it passes through this oil pipe, and see this thing, through the leak it will be releasing the radiation. So you can just detect through the leak, it will be releasing the radiation. You can just detect using Geiger counter. Geiger counter is a machine, or apparatus. I cannot say machine, it is an apparatus using which we can detect the presence of radiation. So if there is no leak, then what will happen? There won't be any leakage, there won't be any radioactive isotopes which is going outside the pipe, which won't be going outside the pipe. So there won't be any radiation. If there is a leak, then obviously there is a passage of this oil. Okay, and ultimately what happens is the radiation will be there outside, and this Geiger counter, it shall be detecting the presence of radioisotopes. Okay, yeah. Now another important aspect is to treat the cancer. There is the cancer is actually the uncontrolled proliferation of cells. Uncontrolled proliferation of cells. Normally our cells, it will be multiplying in a particular level, like say 100 cells per minute, or like total, I am saying total, say not 100 cells, like maybe one cell division per day, or like a two cell division per day, like that it will be happening, not day, usually it will take more than a day. So, but if a cell, it goes on dividing, say like a 5, 10, or like a 20 cell divisions per day, or like say 5 cell divisions per day, this is going to cause cancer. So, uncontrolled proliferation of cells, it can lead to cancer, and that person, he may end up in death. Okay. So now how to control this cancer is, okay, like there is one way you can treat this cancer is, okay, you will be administering this cobalt-60. This is on isotopes. So cobalt-60, like isotopes into our body. So it goes inside the body, okay, and it will go and bind with that cancer cells, and slowly it emits the radiation, and it kills that cell, kills that cancer cell. So there won't be any cancer growth. Okay. And now another one is to kill the bacteria and germs. See, the gamma rays, in fact, gamma rays, it is a very strong and powerful radiation. See, suppose, if I see, this is a food bottle, okay, food gen. So if you pass the gamma radiation, so its outer surface and like inner surface also, it get purified. Say like there won't be any bacteria, any germs, or anything which is passing through here, and it will be completely sterilized, and it shall be completely dry. Okay, so this is something you need to know. So the gamma rays for purifying the medical instruments, say like oxygen cylinder, or like gloves, and then you can say bed. So these surface and all, it should be pure from germs and bacteria. So this gamma rays, if it passes, then normally cobalt-60 and then cesium-137 shall be using for the purification, or like killing the germs and bacteria. Okay, so this is something you need to know. Now, another use of radioisotopes are, the use of carbon-14 for determining the age. So the age of samples. See, we have already seen the half-life of C14. It is 5,700 30 years, right? This is the half-life. Yeah? So now, if you see the, I mean like the fossils, okay. So in order for, suppose you take 100 gram to 50 gram. So just a 50 percentage, right? In order for it to convert into 50 gram, this take 5730 years. Okay. So now, one thing you need to know is, see this much of percentage, you need to take in order for it to reach into 50 percentage. So in a common, I mean like a living body, so whatever the carbon due to the metabolic activity, suppose you consider this is a human body, okay? So human body, so how much amount of carbon it is C14 it is entering, that much amount of carbon C14 it is going, okay? So or else you can say, so do respiration or do the excretion or urination, so the carbon, I mean like, or due to our actions or like energy dissipation, so there will be, we will be consuming carbon. So how much amount of carbon it is going out, okay, how much amount of carbon it is going out, that much amount of carbon it is coming inside also, okay. So this thing you should know. And so due to that, actually the presence of this C14 it remains same in the body. It doesn't change within the human body or like any fossil fuel. Okay. And one thing this is regarding any living body. And once this person or like any animal or like a plant, if it dies, okay. So what happens is, yeah, this process of excretion of, I mean the release of C14 due to the decomposition or say like deterioration or say like degradation, this the release of C14 it goes on happening, but no entrance of C14 will be there because the person or like the fossil it is, I mean like this body, this living fossil it is no longer it is in viable condition. So the entrant of C14 doesn't happen, the release of C14 it goes on happening, okay. Okay, so this is something you need to know. So what happens is, so from the time of death, see the C14 the percentage of C14 it will start to deteriorate, I mean it will start to decrease, okay. From that we need to calculate the age of fossils. So this particular process or like the particular methodology in which we will be using C14 for the detection of age is called carbon dating, okay. Okay, now we can go into some questions. See, what are isotopes? Okay, what are isotopes in the sense any species which is having different neutrons are called isotopes. For example, C13 and C14. Okay, so both are having 6 electrons, 6 proton. Okay, both are, but here it is having 7 neutrons, and here it is having 8 neutrons. Okay, so these two are isotopes, and name the 3 isotopes of carbon and write the symbols for them. Yeah, so it is C12, C13 and C14. Okay, and carbon 14 is radioactive. What does it mean? Radioactive means C14, for example. So this decomposes into beta plus. Okay. Beta, I mean like it decomposes into N14 plus beta plus energy. Okay, so this is the case. And what is radioisotope? Give 2 examples. Radioisotopes are unstable nuclide. For example, same like a C14 or like a cobalt SST. These molecules, it is having decomposition and it decomposes into its energy and different nuclide. We call it as radioisotopes. Okay, and then radiation can kill us. Why? Yeah, radiation can kill us because radiation is nothing but energy. Once it falls on our body, what will happen? Our cells and the body and our tissues and will undergo degradation. Okay, so this is the thing. And next question. So why are radioisotopes used to treat cancer? Yeah, simple thing. Like a cancer cells can be killed by radioisotopes. Okay, and the radioisotopes can be used to check pipe for leaks. Explain how this work. Yeah, so suppose this is pipe, right? So the oil will be running, so there is oil leakage. Okay, suppose if oil leakage happens, so what we initially do is we will just put some radioisotopes into this oil. Okay, and once the oil goes out, okay, so we can detect the presence of radioisotopes through Geiger counter. Okay, so this is the way it works. And next question: spices are shipped all over the world and are often stored for long period. They are usually treated with radiation. Why? In order to kill the germs and bacteria. And name two radioisotopes used for it. Of course, one is cobalt 60. Next one is cesium. Yeah, it is cesium 137. Okay. Yeah.